Hello students, in the previous video we discussed about Z transform and the properties of region of convergence, and we took some examples on how to find the region of convergence and how to locate poles and zeros. In this video we'll discuss on properties of Z transform. So we have I'll just start deriving the properties one by one. So we'll first start with the linearity property. Linearity property here. Now the definition of this is if x of n to perform Z transform gives x of z with region of convergence as R1 and y of n gives y of z with ROC R2, then a x of n plus b y of n, if this is performed Z transform, we'll get a x of z plus b y of z with ROC R1 intersecting R2. Okay. Now, one thing I want to make clear here, you can see this x of z can also be represented in this way, Z transform of x of n. Now, in the same way, so this term a x of n plus b y of n, so you can write it as Z transform of a x of n plus b y of n. So we are going to represent x of z in this way in several times while deriving this property of Z transform. So I am just making this clear. Okay. Now based on this, let's take the proof of that. So Z transform of x of n is nothing but x of z. So that is given by summation n is equal to minus infinity to plus infinity x of n z to the power of minus n. So in the same way, Z transform of a x of n plus b y of n is equal to summation n is equal to minus infinity to plus infinity a x of n plus b y of n z to the power of minus n. So now if you split this, you get summation n is equal to minus infinity to plus infinity a x of n z to the power of minus n plus n is equal to minus infinity to plus infinity b y of n z to the power of minus n. So a and b are constant. If we take that out, so we will leave with summation n is equal to minus infinity to plus infinity x of n z to the power of minus n plus b into summation n equals minus infinity to plus infinity y of n z to the power of minus n. Now these two terms, if you compare with equation 1, so the first one is x of z and second one we call it as y of z. So you can write it as a into x of z plus b into y of z. So here we have started with the Z transform of a x of n plus b y of n. So this is the proof. So the next property is time shifting property. So it says if x of n gives x of z with ROC, region of convergence, as R, then x of n minus n naught after performing Z transform will give z to the power of minus n naught into x of z with ROC as R. So let's take the proof for this. So x of z is equal to summation n is equal to minus infinity to plus infinity x of n z to the power of minus n. So we call this as 1. In the same way, or you can write it z transform of x of n. Z transform of x of n minus n naught is equal to summation n varying from minus infinity to plus infinity x of n minus n naught z to the power of minus n. Now replace this with some other variable. Put n minus n naught is equal to L, so that allows n is equal to L plus n naught. We have to substitute for n here, so that's why. So therefore, we'll get the limit L is equal to minus infinity to plus infinity x of L z to the power of minus. So in place of n, we are replacing this L plus n naught. So L is equal to minus infinity to plus infinity x of L z to the power of minus L and z to the power of minus n naught. Since the limit is L, this term becomes constant. So we'll take this out, z to the power of minus n naught into summation L is equal to minus infinity to plus infinity x of L z to the power of minus L. Now this term, if you compare with equation 1, which is nothing but x of z, so we can write it as z to the power of minus n naught into x of z. Here we started with z transform of x of n minus n naught. So this is the proof for time shifting property. Moving to the next one, scaling, or nothing but time scaling. If x of n gives x of z with ROC as R, then alpha n into x of n will give us z by alpha with ROC alpha R. Here this alpha is a complex number. So here alpha is a complex number. So now based on this, so let's start deriving the proof for this one. Z transform of x of n, which is nothing but x of z, is summation n varying from minus infinity to plus infinity x of n z to the power of minus 1. And here we are taking z transform of alpha n into x of n is equal to minus infinity to plus infinity alpha n x of n z to the power of minus n. Now this z and alpha have same power, so we can combine like this. alpha inverse z to the power of minus n. Now here you have to observe one thing. So coming to this equation, you can see we have x of z here. So if you have z term, so z to the power of minus n is there. And if you take this one, another way of representing z transform of x of n. So this sim input is here. Now coming to this one, if you observe first expression and this expression, we have the same limit, a minus infinity to plus infinity, same input, but here z, in place of z we have alpha inverse z. So that means this can be considered as x of alpha inverse z, or in other words it is nothing but x of z by alpha. So comparing with equation 1, so we have x of alpha inverse z, so which is nothing but x of z divided by alpha. Now to the left we started with z transform of alpha n into x of n. So it says z transform of alpha n into x of n is x of z divided by alpha. So that is the meaning of this. Hence it is proved here, where alpha is complex number. Moving on to the next one, time reversal. So the statement says if x of n gives x of z with ROC as R, then x of minus n will give x of 1 by z with ROC 1 by R. So the proof of this, z transform of x of n, which is x of z, summation n is equal to minus infinity to plus infinity x of n z to the power of minus n. The same way, z transform of x of minus n is equal to summation n equals minus infinity to plus infinity x of minus n z to the power of minus n. Now I'll replace this minus n with some other term. Say put minus n is equal to L. So that gives limit L is equal to plus infinity to minus infinity x of L z to the power of plus L. Okay. Now if I change the limit from L is equal to minus infinity to plus infinity, so then this becomes x of L z to the power of minus L. Okay. No, I think it will remain plus L itself, because plus infinity to minus infinity, it won't change a bit. Now coming to the next step, I can write this minus infinity to plus infinity x of L z inverse of minus L. Okay. Now if you compare this with equation 1, that is here. So we have limit minus infinity to plus infinity. X of L is there. We have x of L here. And here in place of z to the power of minus n, we have z inverse to the power of minus L. So that means we can write this as x of z inverse. Okay. How? By comparing with equation 1. So z transform of x of minus n is equal to x of z inverse, or it can be written as x of 1 by z. So this is z transform of x of minus n, time reversal property. Okay. So moving on to the next one, that is time expansion. So the statement says if x of n gives x of z with ROC R, then x k of n with z transform will give x of zk with ROC R to the power of 1 by k. Now what is this xk of n? Where xk of n is equal to x of n by k if n is an integer multiple of k and it is 0 otherwise. Now to understand this relation xk of n is very important here. Now x of n, xk of n is equal to x of n minus k. So that is the signal here. So in other words, we can write this as x of n by k. If you perform z transform for this, you will get x of z, xz to the power of k. But before going to that, here there is a condition, that is n should be an integer multiple of k, or it will be 0. Why means this is a discrete time signal, and if you take k is equal to 2, just for instance, so you will get x2 of k, sorry, x2 of n is equal to x of n by 2. Now if n is a multiple of k, so that means if I take n is equal to 2, so I'll get x2 of 2 as x of 2 by 2, so that will give you x of 1. And if I take n is equal to 4, then you will get x2 of 4 is equal to x of 4 by 2, that is x of 2, and this will go on. So if it is x, if I take n is equal to 3, then you get x2 of 3, and that is x of 3 by 2 will get x of 3 by 2 means x of 1.5, which is not present. That means this discrete time signal is present only at the discrete instant of time. So we can't have this x of 3 by 2 signal. So that's why it becomes 0. So xk of n will be equal to x of n minus k if n is an integer multiple of 2k. So note that it should be an integer multiple of k. So based on this fact, what I have written, so we can conclude it in this way: x of z is equal to summation n is equal to minus infinity to plus infinity x of n z to the power of minus n. Now if x of z is this, then x of zk can be written as n is equal to minus infinity to plus infinity x of n z to the power of minus kn. So z to the power of kn. So this is the meaning here. And what does it prove? So it's just it says if this input x of n is xk of n for n as a integer multiple of k, so then only the signal exists. So this signal exists only for that value. And here you can see that we are performing time expansion. That means we are it is nothing. Time expansion means the signal size will be enlarged, that means expanded. The signal will be expanded, so some part of the signal will be lost. So those signal which are the multiple of k, that value will be present, and which are not, that value or that signal sample is lost. So that's the meaning of it. Okay, so why this property, we can write it in this way, and we can conclude that the coefficient, this term, the coefficient of the term z to the power of minus n, so this equals to 0 if n is not a multiple of k, and it equals to x of n by k if n is a multiple of k. So that is the justification for this one. And I will take one more here, that is conjugation. So it says if x of n gives x of z with ROC R, then x star of n will give the complex conjugate x star of z with the same region of convergence. So if x of n is real, comma, then x of z is equal to x star of z star. So what is the meaning of this? So this is just a statement. This is nothing to prove here. So it says if x of z, if x of z has a pole or 0 at z is equal to z naught, then it must have a pole or 0 at complex conjugate point. So the complex conjugate point for z is equal to z naught is z is equal to z naught star. So if it is having any pole or 0 at this point in the z plane, then the complex conjugate of that term should also have pole or 0 in that z is equal to z naught star, means in the complex conjugate point of the signal in the z plane. Okay, so that is the meaning of it. So we will continue the remaining properties in the next video. Okay, so if you have any queries, do reply or comment on this video. So thank you for your time.